Hello, everyone, and thank you for coming to this talk at the Mount Cuba Observatory, part of a virtual series of public nights that we're having. Today, I'll be talking about a practical guide to interstellar travel. My name is Dr. Matthew Shultz. I'm the Annie Jump Cannon Fellow at the University of Delaware. That is a fellowship which is endowed by the Mount Cuba Observatory, making it a special honor for me to be here tonight. So when we look at the galaxy, it seems really huge, and it is, several tens of thousands of light years across. But despite that scale, on a very short time scale by cosmological standards, in just a few 100 million years, the entire galaxy could easily be colonized, in fact, just in a few million years. Now, as you can see from the steps in the simulation here, each step takes a few hundred years to complete to establish one colony on a nearby world, and that seems like a long time. And in the course of this talk, I'll show you why that assumption is not terribly pessimistic. This is a fairly realistic assumption for how long it should take interstellar travel to happen. Now, of course, if it only takes a few million years to colonize the entire galaxy, that does raise the question of how come we don't see any aliens out there. And that's an entirely different question, which we will not be talking about today. So there's two primary problems that need to be solved in order to get from our star to another star. The first problem is speed, and the second is distance. So there's a hard upper limit to how fast we can travel. That's the speed of light, 3 million meters per second. Or 300 million meters per second, sorry. It is, as far as we know, completely impossible to go any faster than that, and it's also extremely difficult to even get close to that. There is one way we might get around that, as I'll discuss towards the end of this talk. Now, even if we were traveling at the speed of light, just getting to the nearest star, forgetting for a second about relativistic time dilation, would actually take years, because that's just how large the distance between stars is. And to give you an idea of how large that is in something approaching a human scale, if we were to take the sun and shrink it down to the size of a grapefruit, our entire planet would be about the size of the ball bearing on the edge of a ballpoint pen. And it would be 50 feet away from the sun. Now, on that scale, with our planet being a ball bearing, the nearest star is the same distance from our sun as Washington is from Los Angeles, 2,700 miles away. And that's just the nearest star. And then remember, the entire galaxy is about 100,000 light years across. Well, currently, we actually are an interstellar species. We have two probes that have reached interstellar space. Those are the two Voyager probes, Voyager 1 and 2. They were launched back in the 1970s. On missions to the outer planets. And recently, over the last decade or so, they have started to penetrate what's called the heliopause, which is the boundary between the solar magnetic field region, which kind of forms the outer boundary of the solar system, and interstellar space. And this boundary is not an exactly defined place, so there are actually, you can find several headlines over the course of this time of, oh, we've reached interstellar space. No, now we've reached interstellar space. Well, no, actually now we've reached interstellar space. But we're pretty confident that they're there now. Now, the Voyager probes are traveling at 17 kilometers per second. Now, that's about 17 times faster than the fastest bullets that we have, making them amongst the fastest probes ever launched by human beings. I believe the New Horizons probe is actually traveling faster, but hasn't gone quite as far because it was launched much later. And despite traveling at this absurdly high speed, even if they were traveling towards in the direction of the nearest star, which they're not, it would take them about 100,000 years to reach that star. So clearly, we're going to have to do a lot better than that if we want to become an interstellar species, in a meaningful sense of actually visiting other stars on something approaching a human timescale. So our spacecraft technology currently is entirely based around rockets. So what's a rocket? A rocket basically expels mass in one direction in the form of an explosive combustion of some kind of fuel, and that generates thrust in the opposite direction using Newton's laws. So for each action, there's an equal and opposite reaction. The faster the exhaust, and the more exhaust that you're pushing out, the more the thrust you have. So the thrust is basically just the amount of mass, the rate at which mass is going, and the speed the mass is going at. We use something called specific impulse to measure how efficiently the amount of mass in the fuel is actually turned into a change in the momentum of the vehicle itself. So a rocket fuel with a much higher specific impulse will achieve a higher amount of thrust, a greater change in momentum for a given amount of mass of fuel. Now, rockets have to carry their fuel with them. This is one of the main limitations of a rocket. So for any given fuel with a given specific impulse, if you want to go faster, you need more fuel. And as you add fuel, because you have to carry the fuel with you, your vehicle becomes heavier. The mass increases. So now you actually need even more fuel in order to push it more. This is the essence of the rocket equation, which was worked out back in the 19th century by a scientist named Konstantin Tsiolkovsky, one of the Russian cosmists. And he was a really visionary guy. He actually came up with the idea of space stations that would rotate to create their own centrifugal gravity. He came up with the idea of airlocks so that astronauts or cosmonauts could exit the space station and go out into the vacuum of space. And he even came up with the idea of closed circuit life support systems in order to keep the astronauts alive. He came up with all of these ideas long before the first rocket actually went into space. Now, one of the ways that we try to keep the mass of a rocket down in order to be able to go a little bit faster is to use a multi-stage rocket, which actually was also one of Konstantin Tsiolkovsky's ideas. Now that gets really expensive really quickly because you take this rocket stage, and when it's burned out, you discard it because you don't need it anymore. Okay, that reduces the mass of your spacecraft, so the remaining fuel is able to push it a little bit faster. You know, it's not like that rocket stage is any more use to the mission itself, but it was still very expensive. So just chucking out several million or several tens of millions of dollars worth of rocket technology every single mission gets really expensive really quickly. So a key advance that we've started to make recently, thanks to Elon Musk and SpaceX, is to gain the ability to actually recover and reuse the secondary stages, or sorry, the booster stages. And that really reduces the cost to orbit. Now, if we want a rocket to stop somewhere, say orbit around another planet, we actually need the rocket to be able to slow down a bit, which takes fuel, which adds to the mass of the rocket even more, which takes even more fuel. And you can see how very rapidly this fuel problem in the rocket equation makes missions very difficult to carry out. Now, the rockets that we currently use are chemical rockets, liquid hydrogen, liquid oxygen, various kinds of highly combustible rocket fuels. And these have strong limitations on the amount of thrust they're able to generate on their specific impulse. So one idea that's been floated out there is to use something called nuclear thermal or nuclear electric propulsion, or NTP. So this basically just uses a fission reactor, a very conventional fission reactor, in order to heat liquid hydrogen fuel into a plasma. So we'll have a very high specific impulse, and then channel that into the exhaust. In principle, it's a pretty straightforward idea, and actually NASA was working on an NTP engine called NERVA, the Nuclear Engine for Rocket Vehicle Application, back in the 1970s, with the intention of using this for a Mars shot. This was Wernher von Braun's pride and joy, and unfortunately, the Nixon administration made NASA choose between the space shuttle and NERVA, and NASA chose the space shuttle. So NERVA was put out on a lawn somewhere and has rusted into oblivion and is effectively a lost technology now. But we still know the basics of how to build an NTP engine. And if we were to put something like that together, we could get to Mars in about 3 months, which compares quite favorably to the 6 months it would take with conventional chemical rockets. So that's definitely enough of an improvement to reach the nearest planets in the solar system, but it's clearly nowhere near enough of an improvement to reach the nearest star. Another form of nuclear propulsion is nuclear pulse propulsion. And this is a brutally simple means of propulsion because all you do is you chuck a nuclear bomb out one end of your spacecraft and it blows up, hits a push plate on your spacecraft and accelerates it a little bit. And you carry several hundred bombs with you and you're able to get up to a pretty high velocity. So really scaled down prototype of this, part of the Orion project, was actually successfully tested back in the 50s. Don't worry, this wasn't using nuclear technology. This was using conventional explosives simply to demonstrate that the push plate idea would in fact actually work, and it does. This was the brainchild of an absolute madman named Freeman Dyson. Now, the Orion project was, of course, canceled because the idea of launching a spacecraft into orbit with several hundred nuclear explosions going on underneath it understandably worried people. Furthermore, the idea of simply building one in orbit and then fueling it with several hundred or even several thousand nuclear warheads was concerning to other nuclear powers, principally the Soviets. And of course, the Americans would have been equally concerned if the Soviets were working on such a design. Putting political and environmental considerations out of mind for a moment, an Orion-type spacecraft could actually reach about 5% of the speed of light. Now, you'd need to be quite large for that, about 8 million tons, due to all of the nuclear bombs you need to carry with you. But that would suffice to get you to Proxima Centauri, to the nearest star, in about 80 years. So now we're actually talking on the scale of one human life. It starts to look a lot more doable. And note, we don't need any magic technology for this. We know how to build nuclear warheads right now. Now, if we could achieve fusion propulsion, this gets an even higher specific impulse. So we can go even faster with that. With fusion, the way this works, as opposed to fission where you're breaking an atom apart, with fusion, you're fusing two lighter atoms together in order to create a heavier atom. The fusion technology we have now typically uses deuterium and helium-3, and small pellets of these are injected into the middle of a combustion chamber where they're compressed together using several hundred laser beams, all firing towards the center of the chamber. And when they're compressed enough, the atoms fuse together and you get a very short explosive fusion reaction, and you simply do that hundreds or thousands of times per second in order to get a continuous fusion reaction. This basic technology was worked out quite some time ago, and back in the 1970s, they came up with Project Daedalus, which was a proposed mission that would go to a nearby star, not Proxima Centauri, I forget which star exactly, it was about 10 light years away or so. And it would be a two-stage robotic mission that would take a few decades to reach a nearby star. So the first stage would bring the spacecraft up to 7% of the speed of light and then be discarded as a typical multi-stage mission. And then the second stage would be able to reach 12% of the speed of light. And just to give you an idea of the scale, here's the Saturn V rocket compared to the two stages of the Daedalus mission. The Saturn V rocket being so far the largest spacecraft ever made by human beings, the size of a skyscraper. So this thing would have been an absolute beast and extraordinarily expensive to build, and it wouldn't even have been able to carry human beings to another star. So you can see why we haven't done it yet. But it would be able to reach Proxima Centauri in about 30 years, which is pretty good. It's pretty fast. Now there's other problems with fusion. One of the big problems is that helium-3 is very difficult to find on the Earth, making it quite expensive. So we'd actually need to go to the moon in order to mine enough of it. Now this on its own is not necessarily a bad thing, as it would give us the impetus to start really industrializing the moon, which could really start kicking off our space colonization efforts on its own. But the other problem is that fusion turns out to be a lot trickier than we thought at first. So the old joke goes that fusion has been 20 years away for the last 50 years. And it's only recently that we've actually reached the point where we can get at least as much energy out of a fusion reaction as we put into it. And that's sort of the bare minimum for fusion to be a workable energy generation technology. But if you want to use it for a fusion drive, you have to do a lot better than simply the break-even point. Going a little bit more out there is antimatter propulsion. So antimatter, simply ordinary matter, but with the opposite electric charge. So an electron with the negative charge, the antiparticle is the positron with a positive charge. A proton has an antiproton. Neutrons have antineutrons, and so on. When a particle and an antiparticle collide with one another, they annihilate, and all of their rest mass is turned into energy. So it's a 100% efficient means of turning matter into energy. The result of that is if you had just 1 gram of antimatter, that would be the equivalent of the energy of 23 of the space shuttle's external tanks. There's a lot of matter and energy thanks to that little equation E = mc squared. So with an antimatter rocket, you can get ridiculously high specific impulse, and you could potentially get up to about half the speed of light. That gets you to Proxima Centauri in about 8 years, 8 or 9 years, 4.3 light years away. But we don't really know how to manufacture antimatter efficiently enough. So far, the human species to date has manufactured at enormous expense about 40 nanograms of antimatter. And an interstellar mission, a manned interstellar mission, is estimated to take thousands of tons of fuel. So obviously we need to do a whole lot better on our antimatter generation technology, as it would currently simply be, we wouldn't be able to afford to manufacture enough for even one mission. So all of these technologies, antimatter rockets, fusion rockets, the Orion spacecraft, nuclear thermal spacecrafts, these are all basically just more advanced rockets than we have now. And they all have the same fundamental limitation of the rocket, which is that they need to carry their fuel with them. So you're subjected to the rocket equation, which is quite tyrannous. Obviously, if you could liberate yourself from that constraint, if you didn't have to carry your fuel with you, it's possible that you would be able to travel a lot faster than you would otherwise. And there are certain ideas to do that. One of them is a light sail. Now, this technology works because light, photons, although they are massless, they do carry energy, which means that when a photon hits matter, it is able to impart a little bit of momentum to it. So a solar sail simply uses the light from the sun. And this is a picture of a solar sail being deployed in Earth orbit, I believe by the Planetary Society, just as a test mission to see if as a proof of concept to see if it would work, and it did work, in fact. So the technology seems to be fundamentally sound. And a solar sail would be a really cheap way of moving around inside the solar system if you didn't really care that much about how long it took your spacecraft to get to where it was going. If you want to reach much higher velocities, the kind of relativistic velocities that are necessary to reach nearby stars on a reasonable time span, you're going to need a lot more energy than you're going to get from the sun. A lot more energy density, I should say. And the only way to do that is to propel your light sails with lasers. And there's a proposal to do precisely that. The Breakthrough Starshot project is hoping to send a whole fleet of light sail spacecraft to Proxima Centauri. So the idea is that you would attach to each light sail something called a star chip, which is an entire space probe shrunk down to the size of a single integrated circuit, which contains the antenna, the flight electronics, the sensors, everything necessary to gather information at the destination and return that information to mission control here on Earth. Each light sail would be propelled by a whole array of lasers here on the Earth, which is the only place we can build them because it would take quite a bit of energy to power them. And in principle, we could boost them up to about 20% of the speed of light and get to Proxima Centauri, therefore, in about 20 years, which is kind of cool. If this is pulled off, it means that some of the people watching this might just be alive when humanity's first interstellar mission reaches another star, which is kind of cool. Now, they aren't able to slow down because 20% of the speed of light, you would need an array of lasers on the other end to slow them down. We don't have an array of lasers on Proxima Centauri B to slow down that light sail. So it's going to do a very rapid flyby of the Proxima Centauri system. So rather than just send one probe, we send a whole continuous stream of probes, a whole fleet of them. And each one grabs a snapshot as it does its flyby, beams the information back to Earth, and over the course of several months, we get hopefully quite a bit of information out of it. Now, Proxima Centauri, which is a red dwarf star, we know has a planet which is inside its habitable zone and is similar in size, comparable in size to the Earth. So although it's probably not actually inhabitable for a whole host of reasons, it's still a very interesting target. We could learn undoubtedly a huge amount just with this flyby mission. Now, if we were willing to be a lot more patient, if we could send those probes on a much longer trajectory, much slower trajectory, have them do gravitational assist flybys of Alpha Centauri A, Alpha Centauri B, and then finally actually go into orbit around Alpha Centauri C, i.e. Proxima Centauri. Of course, this would take well over 100 years to reach the final destination. Now, if you don't want to do that, if you want to slow down a little bit more, if you want to travel much more rapidly and then still slow down at the destination, for instance, because you're sending humans on this light sail craft and you want them to colonize that star, then you have some tricky maneuvers to perform. So first of all, you need to have a laser array which does not spread out over interstellar distances. This means you need to be able to build collimators that sort of grab that laser light, which is gradually spreading out just due to physics, and refocuses it along the way. The second thing is that your light sail needs to be able to detach from itself so that when you reach the destination, you're able to fire the laser at the larger sail, which then reflects off of that, hits the secondary smaller sail that your spacecraft is attached to, slows that down enough that your payload can actually enter orbit in the destination system. And this would need to be an absolutely huge light sail in order to propel even a small number of people and the equipment you need to keep them alive and do their mission at the destination. Your light sail is going to be something on the order of hundreds of kilometers in diameter. So another design that doesn't carry its own fuel is something called the Bussard Ramjet. So this is effectively a fusion engine. The main difference being that it doesn't carry its fuel because it simply gathers it from the interstellar medium. Now, normally we think of the space between stars as simply being vacuum, as being just completely empty. And by our standards, it is the density is so low that we actually can't reproduce that density in labs here on the Earth. But there's still stuff there. And predominantly that stuff is in the form of atomic hydrogen. A lot of it is in the form of ionized hydrogen, which means like little protons whizzing around. Now the ionized hydrogen will respond to a magnetic field. So totally forgot. I had a whole thing to explain how the interstellar medium works. So this is a picture of the interstellar medium. So because ionized hydrogen responds to magnetic fields, it has to follow magnetic field lines. If you use a huge magnetic scoop, then you can grab all of that ionized hydrogen and channel it towards your fusion engine. So in this case, you don't need to carry your fuel with you at all. You're just harvesting it as you go. And in fact, the faster you go, the more rapidly you're able to gather fuel. So this design actually increases in efficiency as you go faster. Now, of course, there's problems with this. We still don't really know how to do hydrogen fusion. You'll note earlier in the talk, in the discussion of fusion engines, we were talking about deuterium and tritium fusion, which is all we know how to do right now. The kind of fusion that actually powers the stars remains beyond our understanding, or at least our capabilities. A possible design flaw is that the Bussard Ramjet might actually generate more drag than thrust, and I don't believe this has actually been worked out yet, which of the two is true. If it is true, then the design is simply unworkable. And by far the best option, and the most sci-fi of all of the options, is the Alcubierre warp drive. And this sounds a lot like something from Star Trek, because that's effectively what it is. So the Alcubierre drive utilizes this little loophole in physics. So earlier in the talk, I emphasized that we can't go faster than the speed of light. And that's absolutely true. Matter moving through space cannot exceed the speed of light, period. That says nothing about space. And relativity tells us that space itself can expand and contract. And there's no reason that it can't do so much faster than light can travel. And in fact, in the very early universe, there's an epoch, we believe, known as inflation, during which the universe expanded many, many orders of magnitude faster than the speed of light. So with the Alcubierre drive, what it does is it takes this torus made of something called strange matter, which has negative energy, and you spin it extremely rapidly. And that spinning generates kind of a soliton, a kind of standing wave in space-time. So behind the ship, space expands. In front of the ship, space contracts. The soliton travels through space-time faster than the speed of light, and it carries with it everything that's inside of it, i.e. the spacecraft, which is generating the wave in the first place. And you'll note that the actual ship, there's a little spindle at the center of this design. Space in that region is nice and flat. That's where you put your people and your sort of conventional technology. So space is not warping in the vicinity of the crew themselves. Of course, this technology is very, very far from becoming practical. We have no idea what kind of matter to use in order to build these tori. But theoretical work continues. When the idea was first proposed by Alcubierre back in the early 1980s, it required something like, I believe, the mass energy of the universe to make this work. So it was kind of obviously an absurd idea. But then other theorists have come along and sort of tweaked the design, and one was able to get it down to the mass energy of Jupiter, which is substantially less than the universe, and then the most recent design tweak got it down to the mass energy of a car, which is substantially less than Jupiter. And you'll note that's still a huge amount of mass energy. 1 gram of mass energy is 23 space shuttle external tanks. So the mass energy of a Volkswagen is just huge. But there's a big difference between Jupiter and a Volkswagen. And it's quite possible that future design tweaks could get that amount of mass energy down to something far, far more practical to do. And if at the same time we figure out how to build the strange matter, what that even is, maybe we can make this work. NASA is pursuing this as one of its many sort of more out there possibilities. But for now, we'll assume that we are not going to get an Alcubierre drive anytime soon, and that if we're going to go to another star, we're going to have to do so more conventionally, meaning slower than the speed of light. And that means that most of the designs that we have are going to take an amount, like something comparable to a human lifespan. Like, so even at the speed of light, Proxima Centauri is 4 years away, and slightly more distant stars are, it very rapidly gets up to a human lifespan. Now, of course, if you travel extremely fast, say 99 or 99.999% the speed of light, then relativistic effects kick in. in particular time dilation. So from the point of view of anyone on the spacecraft, time in the external universe starts passing extremely slowly. And they will reach the destination having experienced only a very short period of time. And that amount of time gets shorter the closer they get to the speed of light. So if they were going fast enough, it might only take them a few days, a few hours to reach another star. Although from the point of view of everyone else, it takes them several years, however many light years there are between them and the destination. Now, of course, there's other problems with relativistic travel. Relativity doesn't just dilate time. The mass energy increases dramatically as you get closer to the speed of light, meaning that it gets harder and harder, exponentially harder, to push your spacecraft just a little bit faster. So getting to those relativistic velocities is extremely expensive and very difficult. So if we're not traveling at relativistic velocities, then we can expect that at the very best, a journey to the nearest star is going to take probably on the order of decades and may well take centuries. Not just the nearest star, but any star that is relatively nearby. If it's taking that long, and assuming we don't have some kind of ability to freeze dry humans in cryo chambers, which, by the way, we have no idea how that would even work, then we probably need to send a generation ship. So this is a ship which is large enough that it can support a breeding population of humans. So that means at least a couple hundred humans in order to avoid having sort of inbreeding and genetic drift becoming a serious issue. And it needs to do so for a period of centuries. So that means you need enough air, enough water, and enough food to keep these people alive and healthy until they reach the destination. So this means you need a closed ecosystem able to generate all of this life support, and it needs to work continuously and basically perfectly for hundreds of years. And that stretches our understanding of ecology beyond its limit. We actually did try to do that just for 2 years in the biosphere experiment, and it wasn't successful. Their CO2 levels, or CO2 or carbon monoxide, I think it was CO2, though, spiked through the roof. They weren't able to breathe, and I believe they got overrun with ants. So a closed cycle ecology is a tricky thing to make work. And this is even leaving aside the questions of sociological design required to keep a relatively small society on mission for several human generations. Because as we all know, the dreams of one generation sometimes become the nightmare of the next generation. The sad truth is, at least in our lifetimes, manned interstellar travel is not likely to become anything close to a reality. So, at least for the present, we're probably not going to go to the stars. Our descendants, I believe, almost certainly will, but probably not us. So for now, all we can do is look and try to learn everything we can about the universe without touching. And that's what astronomy is all about. Thank you so much for your attention, and have a wonderful day.